Welcome to this session of questions and answers about lectures 5 and 6. Which of the following is less likely to overfit? The correct answer is C, because the linear model is a simple model, so we are less likely to overfit. Having a large number of features compared to the number of training data points, this leads to overfitting. So we are more likely to overfit in this case. Using a small training dataset, this also leads to overfitting. Selecting hyperparameters, which makes the model as complex as possible, this also leads to overfitting. Which of the following is not a proper way to avoid overfitting? The answer is D. Normalizing the features can lead to better results, especially if the features have different scales. But this is not a way to avoid overfitting. What does an overly complex model lead to? The answer is B. It most likely leads to a low training error. So your model will perform well on the training data, but it will probably not perform well on new unseen data. So here we are talking about overfitting, or low bias and high variance. Why is the cross-validation accuracy a better indicator of the model performance than the training accuracy? The correct answer is C in this case. Why is overfitting more likely to occur when we have smaller datasets? The answer is A, because there is less likelihood of all possible feature values to be observed during the training process. Let's check the other options. So here we have, because in smaller datasets, your validation data is more likely to look like your training data. This is wrong because you will overfit regardless of how much data you will observe in the future. So when you overfit to your training data. So this doesn't make sense. Let's check this option, because if we take a neural network, for example, there isn't enough data to activate all neurons. That's wrong. That doesn't make sense. And this option, because with less data, the training will take place more quickly, and some features may be missed. That doesn't make sense too. Choose among the following options the most reliable way to estimate the generalization error of a machine learning model. The answer is D. So this corresponds to what we saw in the lecture. This is using the k-fold cross-validation. One way to do feature selection is to select the right answer, normalize the data, and then remove features having a low variance. And when I talk about normalizing the data here, I'm talking about using the min-max scalar. So you want, for example, your feature values to be in the interval 0 to 1. And here you should not normalize the data by subtracting the mean and then dividing by the variance or the standard deviation. Because if you do that, then all features will have the same variance, which is 1. Okay? And the motivation behind removing features with a low variance is that such features are not informative. For example, if you have a feature where all the values are the same, regardless of the example we are talking about, then this feature will have a variance of 0. And such a feature is not informative because it doesn't help differentiating between different examples. And if we check the option C, train a linear model, theta 0 plus theta 1 x1 and so on, then remove the features xj having a large coefficient theta j. Well, what we should do is actually the inverse of this. You want to remove features having a low coefficient theta j, because such features will not contribute much to this prediction. Select the correct statement about regularization. The answer is A. It generally increases the training error, but the generalization error will most likely be lower. So you get a better model with regularization, given that you fine-tune correctly the hyperparameter used for regularization. Consider this cost function used for linear regression, and then choose the correct answer about the effect of the hyperparameter lambda. The correct answer is D. If lambda is too small, then overfitting can happen. For example, extreme case, if lambda is equal to 0, then we don't have this term. So we don't do regularization. And we focus only on minimizing the mean squared error. And in this case, overfitting can happen depending on our data set. For example, if we have a lot of features and few data points, then overfitting can happen. On the other hand, if lambda is set to an extremely large value, then underfitting can happen. So here, if lambda is extremely large, then the only way to minimize this cost function is to choose parameters theta j, which are very small. And as lambda goes to infinity, those parameter values that you will find will be closer to 0. So you will get a poor performance model. Read this description about these two figures and then select the right answer. And the correct answer is D. So the first model that we got B for, this one, was probably a regularized model, while in the second model, this one, we didn't use regularization. So we got a complex model which overfits to the training data. So what is the optimization problem associated with the soft margin SVM that we saw in the lecture? The correct answer is B. So we want to minimize the magnitude of those parameters, which actually means that we want to maximize the margin. And this is the hinge loss, and we want, by minimizing it, we want to classify correctly most of the training data points. And there is a trade-off parameter between this objective and this one. So we have this hyperparameter C to make this trade-off. And we have discussed the effect of this hyperparameter in lecture 6. If we look at option A, we want to maximize this, and this is the equation of the margin. So we want to maximize the margin subject to classifying correctly all the training examples in our training data set. So this is a hard margin because we have this strong constraint that we want to classify correctly all the training examples. So that's a hard margin. And if we look at option C, this is the mean squared error. So this is not what SVM minimizes. So the correct answer is B. This is related to the previous question. So suppose that we want to learn a linear classification model by minimizing this cost function. And this is the cost we used for a soft margin SVM. So what would be the effect of the hyperparameter C on the classification model for the dataset illustrated in this figure? The correct answer is A. So if C is not too large, then the resulting model will tolerate misclassifying the red data point that we have here. So we will get a model which maybe looks like this. Because when C is not too large, then we are also given importance to minimizing this part here. And minimizing this part means we want a large margin. But if C is very large, then the model that we will get will most likely classify all the training examples correctly. So maybe we will get a model like this one. And such a model will have zero error on this training dataset, but it can fail to generalize to new unseen data. For example, if you get a new data point here which should belong to the blue class, then this model will classify it as belonging to the red class. And same thing if you get data points here that should be in the red class, they will be classified as belonging to the blue class. And you can check the lecture for more information about this. Read this description here, and then given this confusion matrix, what will be the classifier's accuracy? Accuracy is just the number of data points that are correctly classified divided by the total number of data points. So the correct answer is A. So in this case, we get a very low accuracy. True or false, a model with more parameters is more prone to overfitting and typically has a higher variance. Yes, because usually more parameters means a more complex model. Is it true or false? If a learning algorithm is suffering from high bias, then only adding more training examples may not decrease the test error significantly. That's true. A high bias means that we are probably underfitting, and so adding more training examples will not help much. This will help more if you are overfitting. In which of the following figures do you think that the hypothesis has underfit the training dataset? And the answer is D. In figure 1, the model looks okay for this dataset. The same for figure 2, it looks okay. In figure 3, we are probably overfitting a little bit. And here we have underfitting. So this model is not as complex as what it should be. It does not capture the complexity of the data.